Hello and welcome to today's video. Today I'm going to show you how to apply change of variables to an example. We'll start with an example using polar coordinates in the plane. So one of the main applications of polar coordinates is the description of regions that have, let's say, a circular character. And the example that we're going to look at now is such a domain. So we're going to look at the set X that is defined as all X in R2, where X1 is positive, and at the same time the norm of X squared is between 1 and 4. The function that we are going to look at is defined on this domain X, and the function term is x1 times x1 squared plus x2 squared. Now let's first have a quick look at how this domain looks like. So here's a sketch. What these two conditions here say is the first one, x1 is positive, so we are on this side of the coordinate system. What this condition here says is that the norm squared is between 1 and 4. So the norm itself, without the square, will be between 1 and 2. That means we have a region that is restricted to the right side of the coordinate system. And that is basically a circle with an inner radius of 1 and an outer radius of 2. So it's not quite a circle, it's a disk. Yeah, just the outer part of a circle. So the radius is larger than 1 and smaller than 2. So this region here, the set X, looks somewhat like this. So X is a half ring with inner radius 1 and outer radius 2. Also, if you have a look at the function definition here, then you will clearly see that this latter part here, that exactly is the norm of X squared. So not only the domain can be described conveniently in polar coordinates, also this norm and therefore the radius in polar coordinates plays an important role in the function term. So the function itself is more conveniently described in polar coordinates as well. Okay, so the domain and also the function can be described conveniently through polar coordinates. So what we have here, if we are going to describe X in terms of polar coordinates, remember if you have polar coordinates r and phi, so a radius and an angle in the plane, then you can compute the corresponding Cartesian coordinates through r times cosine of phi and r times sine of phi. And if you use those terms r, radius, and phi, angle, to describe this half ring, then what you get is the radius is always between 1 and 2, right? Radius is this here, so that always varies between 1 and 2. And the angle, well, the angle of a point is basically this part here, so that's phi. And that varies between this angle here, that is pi over 2, and this angle here, and that is minus pi over 2. So we have minus pi over 2 less than phi less than pi over 2. And you can see in terms of polar coordinates, those two variables, radius and angle, r and phi, those are independent of each other. So in terms of polar coordinates, such a ring has the characteristics of a box. And of course, for integration, it's much more convenient to integrate over a box than over a normal domain with complicated descriptions. So we'll do just that. We'll reformulate the integral using change of variables to integrate over polar coordinates instead of over Cartesian coordinates. So we want to evaluate the integral of f of x dx over x, but we want to do that using polar coordinates. Now what do we need for that? First thing we need is the transformation. That is a mapping we call G that transforms from polar coordinates to Cartesian coordinates. We know that mapping already, we've just used it. So G of r and phi is r cosine phi and r sine phi. So for polar coordinates r and phi, the corresponding Cartesian coordinates are these here. We also need the domain in polar coordinates. So we need a domain D such that G of D will be X. And this domain is easily described. We have done that already as well. It consists of all radii and angles r phi such that r is contained in the interval from 1 to 2. And phi is contained in the interval from minus pi over 2 to pi over 2. So that's the domain in polar coordinates. And using that we get G of D is equal to X. And of course this transformation function G is injective on D. And it's also continuously differentiable. And furthermore, we also need the actual differential. So let's determine the Jacobi matrix of G and the determinant of that matrix. Now for the Jacobi matrix, if we differentiate G, here's G once again, if we differentiate that with respect to R, then what we get is the cosine of phi and the sine of phi. And if we differentiate with respect to phi, Then in the first row we get minus r sine of phi, and in the second row we get r cosine of phi. So here's the Jacobi matrix, and let's compute the determinant. The determinant of the matrix is then r times cosine of phi squared plus r times sine of phi squared. Now, a little abbreviation that I'm going to use frequently in the following, because these are cosine and phi, and there's 11. Now, a little abbreviation that I'm going to use frequently in the following, because terms like cosine phi to the power of 2, 3 or something, and sine phi to the power of 2, 3 or something, those will appear frequently in the computations with polar coordinates or spherical coordinates or cylindrical coordinates. So to make things a little easier to see and to make things a little easier to write, there is a common abbreviation for terms like this: cosine phi squared, cosine phi to the third, to the fourth, and so on. You abbreviate that by cosine squared phi, like that, right? So that means the same thing. And of course, you can use the same notation for the sine, like this. Just please don't confuse that with the repeated application of the function. So cosine squared phi means cosine phi squared. It does not mean cosine of phi. Yeah, well, that would be mathematically, that would be more satisfying, or maybe more correct. That's unfortunately, that is not what is commonly meant here. Okay, and it will turn out, as these terms appear quite often in the following, this is probably much easier to read and to write. So I'm going to use that notation from now on, at least in this context here. Okay, so one more step. This is the same thing as r cosine squared plus sine squared. And as you know, cosine squared plus sine squared of an angle is 1. So this is just r. Okay, and the radius is positive anyway, so the absolute value of that radius is also the radius. And now we are prepared to actually compute the integral. Now recall what we do here. We want to integrate f of x dx over x, and by the change of variables theorem, that is the same thing as integrating f of g of r and phi over d times the absolute value of the Jacobi of g at r and phi d r phi. So for our function and for our domain, what does that mean here? We've seen already that d is composed of all radii between 1 and 2. So let's take this as the outer integral. And all angles between minus pi over 2 and pi over 2. So we'll have this double integral here. The function f, remember, f of x is x1 times x1 squared plus x2 squared. And also remember g of r phi is r cosine phi, r sine phi. So x1 is r cosine phi. And that means if we want to express f of x1, x2 in polar coordinates, then what we get here is, I'll write this way once more, so we get f of r cosine phi and r sine phi. And then we multiply this with the absolute value of the determinant of jg. I'm sorry, the determinant is missing here. So that is an r, and we integrate d phi dr. So let's substitute the definition of f in here. Remember, here's the definition of f once again. So we have x1. x1 is r cosine of phi times x1 squared plus x2 squared. That is r squared cosine squared phi plus r squared sine squared phi times r d phi dr. So what we have is, simplify this a little more. So we have one r here, r squared. We can take this r squared out here, and one more r here. So altogether that's r times r squared times r. So what we're getting is an r to the fourth. We're also getting this cosine of phi here. And then this expression here, that is, we already took out this r squared, so this expression becomes cosine squared plus sine squared, and that is again 1. So that's r squared times 1 here. Okay, so that is our function, or our integrand, in terms of polar coordinates now. And that means the integration itself becomes pretty straightforward. We'll have to integrate this r to the fourth in the next step. Let's start with the cosine, the inner integral first. So the integral of the cosine is the sine of phi, for phi from minus pi over 2 to pi over 2 dr. And so what we get here is the sine of pi over 2. Remember, the sine basically looks like this here. Here's pi over 2. Here's 3 pi over 2. Same thing if we go into the negatives. Yeah, here's minus pi over 2. So what we get here is a value of 1 for pi over 2, and a value of minus 1 for minus pi over 2. So that's minus 1 dr. So finally what we have is 2 r to the fourth dr. And so finally we have 2 r over 5, r to the fifths over 5, r from 1 to 2. So we get 2 times, let's see, that is 2 to the fifths minus 1 to the fifth, that's 1 over 5. So what we get here, 2 to the fifths, that is 32, right? 8, 16, yeah, that's 32. Minus 1, that is 31 over 5 times 2. So we end up with 62 over 5. And that's the final result for this example here. So as you can see, using polar coordinates makes the description of the domain a lot easier. And in this case, it also made the function itself a lot easier. The downside of this, of course, is that we have to compute this Jacobi matrix here, and we have to compute this determinant here. But on the positive note, we only have to do this once. Now that you know about this, whenever you use plane polar coordinates again, you already know this determinant here. That is just r. And you can, of course, just use that knowledge without doing the computations again. Yeah, so those steps here, what we did here and what we did here, this only has to be done once. And from now on, you just use your knowledge, substitute r whenever this term here occurs, and you're good. Okay, in the following videos, we're going to see some more examples. Specifically, there'll be one on spherical coordinates. And then we'll have a look at other types of integrals as well.